Hello everyone, I am Rama. In this video I am going to explain you what is a cubic spline interpolation. Before that, let us define what is a spline interpolation. The definition is, instead of considering a single higher degree polynomial over the interval closed interval a comma b, we subdivide this into subintervals and consider many lower degree polynomials over each subinterval. Then we get an interpolation function which is called a spline, and then by fitting them into a single curve over the interval a comma b. Thus, the spline interpolation is said to be a piecewise polynomial interpolation. Suppose that our given data is xi, yi. We write x values from 0 to n. That means our data is like x0, y0, x1, y1 and so on, xn, yn. There are n plus 1 data points. Usually in interpolation, using n plus 1 data points, we can fit a single curve which is of degree less than or equals to n. But here we are going to subdivide this interval a comma b into subintervals such as x0, x1, x1, x2, x2, x3 and so on. The last subinterval is xn minus 1 comma xn. Here these x values may not be equally spaced, and then in each subinterval, that means in the interval x0, x1 and in the interval x1, x2 and so on, in each subinterval we can find a polynomial which is of any degree. That means degree 1, degree 2, degree 3, etc. So that is shown in green color here. In a similar way, we can find a polynomial of degree anything in the next subinterval x1, x2, that is taken as s2 of x. In the first subinterval, the spline function is s1 of x. In the second subinterval, the spline function is s2 of x, and so on. In the last subinterval, the spline function is denoted by sn of x. Here, our spline interpolation is nothing but we need to find these s1, s2 and so on in each subinterval. So, our s of x can be expressed as s1 of x over the interval x0, x1, s2 of x over the interval x1, x2 and so on, sn of x over the interval xn minus 1 comma xn. Then how to find this s1, s2 and so on, sn. Thus, the spline function s of x is said to be a continuous function that has the following properties. First one, the spline must be passing through all data points. It means that s of xi must be equals to yi, where I is taking values from 0, 1, 2, 3 and so on, n. For example, if we take first subinterval x0, x1, then our spline function must be satisfying the condition that s of x0 equal to y0, comma s of x1 equals to y1. Then what is our s of x0? x0 is in the first subinterval. In this interval, s of x is equivalent to s1 of x, so which is obtained from s1 of x0. Similarly, s of x1 equal to y1, again in first subinterval, x1 is there, so s of x should be taken as s1 of x. So it must be equivalent to s1 of x1. Similarly, to each subinterval, if we take x1, x2, then it must be satisfying that s of x1 equal to y1 in the sense second subinterval x1, the value which is obtained from s2 of x1. Similarly, at another point, s of x2 must be equivalent to y2. Again, x2 belongs to second subinterval, so it can be obtained from s2 of x. So it can be written as S2 of x2 and so on. It should be true in each and every subinterval. Now the second point is S of x is a polynomial of degree n or less than that in each subinterval. Xi minus 1 comma xi, where I is taking values from 0, 1, 2, 3 and so on. Now the third point is S of x, S dash of x, S double dash of x and so on, S n minus 1 of x must be continuous at each internal point. So this is the actual definition of spline interpolation. But here we want to fit cubic splines over the given interval, closed interval a comma b. Then how to define it? Cubic in the sense it is a degree 3 polynomial. So in each and every subinterval we are going to get a polynomial of degree 3. Hence the spline interpolation is said to be cubic spline interpolation. So here we can again write three conditions as spline function must be satisfying all the data. That means S of xi equals to yi. And second point is S of x must be a polynomial function of degree 3 or less than that. And third condition is S of x, S dash of x, S double dash of x are continuous in that means at each internal node. That means at x1, x2 and so on, xn minus 1. Cubic spline function si of x on general interval xi minus 1 comma xi is obtained from the formula si of x equal to 1 by 6 hi into xi minus x whole cube into mi minus 1 plus x minus xi minus 1 whole cube mi plus x minus xi minus 1 by hi into yi minus hi square by 6 mi plus xi minus x by hi into yi minus 1 minus hi square by 6 mi minus 1, where I is equals to 1, 2, 3 and so on n. If I give I is equals to 1, then I will get S1 of x in the first subinterval. For I equal to 2, I get S2 of x in next subinterval, that means second subinterval and so on. And hi equals to, which is the length of the interval xi minus 1 comma xi. That means hi equals to xi minus 1 and mi, which is the second derivative of s at each x, that means xi. So here we are going to fit natural cubic splines. While finding natural cubic splines, we have to set conditions at endpoints. Then what are the conditions? We have to set m naught, which is nothing but s double dash of x naught as 0, and then mn, this is the last point, which is nothing but s double dash of xn, which is also 0. So we have our data from x naught to xn. So we have taken m naught mn, that means second derivative of s at endpoints is set as 0, Now we need to find m1 at x1, m2 at x2 and so on, mn minus 1 at xn. That means there are n minus 1 unknowns. These are to be determined for which we use a recursive formula hi mi minus 1 plus 2mi into hi plus 1 plus mi plus 1 hi plus 1 equal to 6 by hi plus 1 into yi plus 1 minus yi minus 6 by hi into yi minus minus 1. Here we must take I values as we have to find m1, m2 and so on mn minus 1. We can take these suffixes starts from 1 and ends at n minus 1. So we must give I values as 1, 2, 3 and so on n minus 1. And then we can see hi plus 1 in the formula. Hi is nothing but length of the interval xi minus 1 comma xi. So hi is nothing but xi minus 1, so that hi plus 1 equal to xi plus 1 minus xi. Now by giving these I values in this formula, we can generate n minus 1 system of linear equations. This can be solved for m1, m2 and so on mn minus 1. Right? While finding cubic spline functions, we must remember the steps as follows. In step 1, we need to find m1, m2 and so on mn minus 1 by setting the conditions m naught equals to mn equals to 0, for which we use the recursive formula that is shown here. After obtained m values, in the next step what we will do is use m values in Si of x, so that we can find s1 of x in first subinterval, s2 of x in second subinterval and so on. We proceed the same up to the last subinterval, and finally we have to express s of x as a piecewise polynomial function. So s1 of x will be s1 of x in the interval x naught x1 and s2 of x in the interval x1 x2 and so on. Usually for n plus 1 data points, we will find n spline functions, n cubic spline functions. So let us do one problem. Fit a cubic spline to the data. X values 0, 1, 3, y values 1, 0, 2, and hence find f of 0.5, f of 2, integral 0 to 3 f of x dx. So whatever the given data is, whether it is equally spaced or unequally spaced, we should take our data as the set of xy values should be taken as x0 y0, x1 y1, x2 y2 and so on. Here we have from x0 y0 to x2 y2. We are just taking the values as x0 is 0, y0 is 1, x1 is 1, y1 is 0, x2 is 3, y2 is 2. It is very clear there are 3 data points. For these 3 data points, you can see 2 subintervals x0 to x1, x1 to x2. Now let us find the length of each subinterval. h1, which is the length of first subinterval, which is x1 minus x0. So it is 1 minus 0, nothing but 1. And h2 is equals to length of second subinterval x2 minus x1, 3 minus 1, which is 2. Now we have to set condition for natural cubic splines. starting point is x0, ending point is x2, so we have to set m0, m2 as 0. In between we have only one internal point. At this point we need to find m value, that is m1, for which we need to consider recursive formula. The formula is hi mi minus 1 plus 2 into hi plus 1 into mi plus hi plus 1 mi plus 1 equal to 6 by hi plus 1 into yi plus 1 minus yi minus 6 by hi yi into yi minus 1, where we must give I is equals to 1 only, because we want to get only m1 at one internal point x1. So by giving I equal to 1 in this formula, let us rewrite this again. Then it becomes h1 m0 plus 2 into h1 plus h2 into m1 plus h2 m2 equals to 6 by h2 into y2 minus y1 minus 6 by h1 into y1 minus y0. Now let us use all the known data. Since m0 is 0, 0 into anything will become 0, plus 2 into h1 plus h2. h1 is obtained as 1, h2 is obtained as 2, so it is 2 into 1 plus 2 m1 plus m2 is 0, so the term becomes 0, that is equals to 6 by h2 is 2, so 6 by 2 into 2 minus 0 minus 6 by 1 into y1 is 0, y0 is 1, so it is 0 minus 1. Now this becomes 2 into 3 6 m1 equals to 3 into 2 minus 6 into minus 1, so this becomes 6 m1 equals to 12, then m1 equals to 2. In the next step, we need to use these m values to get spline pieces in each subinterval. So this is our general formula. As we have two subintervals, we will get only two spline functions, for which we have to give I is equals to 1 comma 2 in the general formula. So let us give I equal to 1 in this and write s1 of x on first subinterval x0 x1, that is on the interval 0 comma 1, so that s1 of x is going to be 1 by 6 h1 into x1 minus x whole cube m0 plus x minus x0 whole cube m1 plus x minus x0 by h1 into y1 minus h1 square by 6 m1 plus x1 minus x by h1 into y0 minus h1 square by 6 m0. Now in this we will use all the known data, so that s1 of x is equals to 1 by 6 into, as h1 is 1, 6 into 1 will become 6 only, so it is 1 by 6 into x1 is 1, the x will be as it is 1 minus x whole cube into m0 is 0, so the entire term will become 0, so no need to write that again. And the next term is x minus x0 is 0, so it is x minus 0 whole cube into m1 is obtained as 2, the term is over, plus x minus x0 is 0 by h1 is 1 into y1 0 minus h1 is 1, so h1 square is also 1 by 6 into 2, so x minus 0 by 1 into 0 minus 1 by 6 into 2. The next term is x1 is 1 minus x by h1 is 1, y0 is 1 minus h1 square is 1 by 6 into m0 0. Now we need to simplify this. Here we have 1 by 6 into x cube into 2, 2x cube. So after the cancellation, this becomes 1 by 3 x cube. This is over, and then here we have x by 1 is x into minus 1 by 3, so it is minus x by 3. This term is over, plus 1 minus x into 1, simply 1 minus x. Now by regrouping the terms, it will be expressed as, after taking LCM, it can be expressed as 1 by 3 into x cube minus 4x plus 3. This is our s1 of x. Now we will find s2 of x on interval x1 comma x2, that means in the interval 1 comma 3, for which we will put I is equals to 2 in this general formula, so that s2 of x will be written as 1 by 6h2 into x2 minus x whole cube m1 plus x minus x1 whole cube m2 plus x2 minus x by h2 into y1 minus h2 square by 6 m1 plus x minus x1 by h2 into y2 minus h2 square by 6 m2. We can use all the known data here, so that s2 of x equals to 1 by 6 into h2 is 2, 6 into 2 is 12. So 1 by 12 into m1 is 2, so 2 into x2 is 3 minus x whole cube plus as m2 is 0, the entire term will become 0, so this term is closed, plus x2 is 3 minus x by h2 2 into y1 is 0 minus h2 square, 2 square is nothing but 4 by 6 and m1 is 2 plus x minus x1 is 1, h2 is 2, y2 2, h2 square 4, m2 0. So this term becomes 0. So we have substituted all the known data in this, so that this is going to be 1 by 6 into 3 minus x whole cube minus 4 by 6 into 3 minus x plus x minus 1. Now by simplifying this, we get the polynomial 1 by 6 into minus x cubed plus 9x square minus 17x plus 9. So that we can express our s of x as s1 of x is nothing but 1 by 3 into x cube minus 4x plus 3, which is over the first subinterval 0 comma 1, and s2 of x equal to 1 by 6 into minus x cube plus 9x square minus 17x plus 9, which is over the interval 1 comma 3. So here these functions s1 s2, s1 is over the interval x0 x1, so that it must be satisfying the condition s1 of x0 equals to y0, s1 of x1 equals to y1. Similarly, our s2 of x is over the interval x1 x2, so it must be satisfying the condition s2 of x1 equal to y1 and s2 of x2 equals to y2. That you can check. Here my function is satisfying these conditions. You can also check it. So we got cubic spline function. We have some other bits, and hence using the spline we need to get f of 0.5. f of 0.5. We need to check in which interval this 0.5 lies. It is very clear it lies between 0 and 1. So in the first interval our s of x is equal to s1 of x. So f of 0.5 can be obtained from s1 of 0.5. In this polynomial we put x equal to 0.5 and we get the value as 0.375. Similarly, the next bit is f of 2. Here we want to get f at x equal to 2. X equal to 2, that lies between 1 and 3, that is in the second subinterval. So s of x must be taken as s2 of x. So f2 is obtained from s2 of 2. In this polynomial we will put x equal to 2. So we are getting the value as 0.5. Now the third bit is we have to find the integration of f of x from 0 to 3. F of x is not a single polynomial, it is obtained as which is equal to s of x and which is piecewise polynomial function. So we have to split the interval 0 to 3 as according to our data. So it is from 0 to 1 and then 1 to 3. In the interval 0 comma 1, f of x in the sense s of x, which is equal to s1 of x. So f of x is replaced by s1 of x. And in the second subinterval 1 comma 3, our f of x is equal to s2 of x. Now in the first integration we use s1 of x, in the second integration we use s2 of x. Now by doing normal integration and applying the limits, we get the value as 7 by 4. That means integral 0 to 3 f of x dx is obtained as 7 by 4. The same we can extend to any number of data points. I hope you understood this. Thank you.